So the pH is not the only way of assessing the strength of an acid. If you look up here, if we refer to the dissociation reaction for an acid and the dissociation reaction for a base as equilibrium systems, we're able to write a law of mass action for either the acid or the base. The law of mass action for an acid dissociating looks like this, and the law of mass action for a base dissociating looks like this on the bottom. Each of these respective laws of mass action equal their own K value. The K value for an acid is called a Ka value, and the K value for a base is called a Kb value. Using these law of mass action equations, we will be able to assess how much an acid or base actually dissociates based on their ratios of product to reactant. And this is the scale we will use to determine how strong or weak an acid or base is. As you can see by looking at these laws of mass action, a large Ka value comes from having a large concentration of H+, also written here as H3O+. And a large Kb value comes from having a large concentration of OH-. Just as in the last chapter, a large value indicates a product-favored reaction, and a small value indicates a reactant-favored reaction. Let's take a quick look at the relationship between these two ionization constants, the Ka and the Kb. If you look in your book at the table which lists various Ka and Kb values, you will find the values listed for carbonic acid. If you look at the table, you'll find the Ka is 4.2 times 10 to the minus 7th, and its conjugate base has a 2.4 times 10 to the minus 8th. If we multiply these K values together, we get 1.0 times 10 to the minus 14th, which should be a pretty familiar number. This is a relationship that you can test with any of the acid conjugate base pairs in the table. The conclusion you can then draw is that Ka times Kb equals Kw, which is the 1.0 times 10 to the minus 14th. A sub-conclusion that you can draw from this, which is very important, is that the large value of Ka, the larger the value of Ka, the smaller the Kb value needs to be in order for their products to still equal Kw. Put another way, the stronger the acid, the weaker its conjugate base. The stronger the acid, the weaker its conjugate base. Super important concept. Let's take this idea a little bit further. If we take a reaction such as the reaction of phosphoric acid with sodium acetate, we get something that looks like this. When we assess this, we find that phosphoric acid is the acid, and the acetate ion, or sodium acetate, is the base. And on the other side, we find that the acetic acid is our conjugate acid, and the dihydrogen phosphate, this ion right here, is our conjugate base. Because in the reverse direction, the acetic acid would act as the acid, and the dihydrogen phosphate would act as the base. If we pull up the K values, and just so that you know, if it's an acid, I listed its Ka value, and if it's a base, I listed its Kb value. Put those in blue. If we assess these, let's start with the acids. We have 7.5 times 10 to the minus 3rd, and 5.6 times 10 to the minus 10th. You can see pretty readily that this one has the bigger number. It's therefore the stronger acid. And if you look down at our bases, you can see pretty readily that, let's see, this one has the bigger number, and it's therefore the stronger base, which makes this whole side a stronger side than the right-hand side. Thus, because of this assessment, you can tell that the equilibrium position would lie far to the right, the product side, and that this reaction would produce a lot of dihydrogen phosphate ion and acetic acid, because the reaction will proceed from the stronger acid-base combination to the weaker combination. Remember that to be stronger is to dissociate more. Let's pause and talk about the types of problems that you should be able to solve at this point. First of all, you should be able to write the Ka expression for a compound such as HCN. If you look at this compound, in order to write the law of mass action, you need to be able to write its dissociation. You can quickly write this, or write it in sort of an abbreviated way, like this. And this is what I would expect to see. Or for this next one, which you are probably totally unfamiliar with, but in order to write the dissociation, you simply have to peel off an H+. C6H5. You would then be able to write a law of mass action for each of these reactions.